Right now, the entire digital universe, every video, every photo, every email, every website, demands enough power to run 100 million homes. It fills continents with data centers and burning through electricity just to exist. But what if I told you that by the end of this video, we could actually fit all of it, the entire internet, inside a single grain of sugar with zero power? Right now, as you watch this video, thousands of miles away, a server is screaming. It's burning through electricity and pushing massive amounts of heat into the atmosphere just to keep a digital file alive. By the end of this decade, global data center capacity is projected to hit 200 gigawatts. That's enough to power 100 million homes. We are currently creating more data in the next 3 years than we have in the last 30 combined. We are being hit by a data tsunami, and we are literally paving the planet with silicon just to keep up. But we're hitting a wall. Silicon transistors are reaching the size of a few atoms, where the laws of physics break down. We have reached the physical limit of the machine. But what if the solution isn't a machine at all? What if it's a single drop of liquid? Welcome to the dawn of molecular computing. For the last 70 years, computing has been a game of incrementalism. We like to think that the explosion in AI and GPUs represent a fundamental leap, but even the most powerful chips today are just evolutions of the same architecture from the 1950s. They still rely on moving electrons through tiny gates on a flat piece of silicon. AI hasn't changed the physics of computing. It has just optimized the math. Jensen Huang often talks about first principles thinking, stripping a problem down to its most basic physical truths. If we apply that here, we realize the problem isn't the chip design, it's the medium. Electrons are leaky, silicon is 2D, and the heat is an inevitable byproduct of resistance. To get the next 1,000-fold increase in efficiency, we can't just improve the GPU. But here's the exciting part. With silicon, we had to build the plane while it was already flying. We had to invent the physics, the factories, and the software, all at once. With molecular computing, we get to leapfrog that struggle. So how does this biological computer actually work? We are using 70 years of silicon advancements, our most powerful AI and most precise robots, to cheat the development cycle of biology. We are using the old plane to build the new one. Your computer speaks in binary, ones and zeros, but biology speaks in quaternary. In molecular storage, we map our digital data onto the 4 chemical bases of DNA: adenine, cytosine, guanine, and thymine, or A, C, G, and T. DNA is so dense that you could store every movie ever made in a volume smaller than a grain of sugar. But think of it like a time capsule. If you're writing an email and make a typo, you hit backspace. In molecular storage, once that DNA is synthesized, it's set in stone. To fix a typo, you'd have to reprint the molecule. It's slow and deliberate. You wouldn't use it for a grocery list, but if you wanted a message to survive for 10,000 years, the time capsule is the only tool for the job. We are trading the editability of silicon for the immortality of chemistry. In computing, volatility is a feature. The data on your RAM doesn't survive a reboot, and it shouldn't. It needs to be a blank slate for the next task. Your hard drive or SSD isn't meant to last 100 years, and it doesn't. It's designed for the high-speed cycle of a human career. Silicon is built for the now. But what about data that needs to outlast us? When we look at the data that defines our species, we need the opposite. In 2021, scientists sequenced the genetic code of a woolly mammoth that died over 1.2 million years ago. That DNA sat in the frozen dirt of Siberia with zero power and zero maintenance. Molecular storage is nature's black box. It is the only storage medium in the universe that can survive an ice age and still be readable. We aren't trying to make DNA behave like RAM. We are using it for exactly what it was designed for, the permanent record of life. Molecular storage is a 0-watt storage. But there's a deeper link here. Molecular storage is the perfect partner for quantum computing. Quantum computers are insanely fast, but they have a memory problem. Qubits are fragile, and they decohere, or forget their state in milliseconds. Because molecules are themselves quantum objects, researchers are now looking at DNA-based quantum memory. Recent research suggests that we can use quantum algorithms to map and search molecular data at speeds silicon can't touch. If a quantum computer is the world's fastest brain, molecular storage is its permanent, long-term memory. Once written, it stays stable for centuries without needing electricity. Currently, 60 to 80% of the world's data is what we call cold data. These are files that we rarely access but cannot afford to lose. For example, high-resolution medical scans tracking the evolution of diseases, global financial ledgers and land deeds, or scientific data from the Large Hadron Collider. Right now, we spend an astronomical amount of energy just keeping the lights on for this data on magnetic tapes. If we move just half of this archival data to molecular storage, we could reduce the global energy demand of data centers by 40%. We'd be moving from a world where we rent our history with a monthly electricity bill to a world where we own it forever in a vial. But if our secrets are in a vial, what stops someone from stealing it? Molecular storage uses chemical steganography. To a thief, a vial of data looks like salt water. You could hide the blueprints for a jet engine inside the bottle of perfume, or in the ink of a printed book. There's no scanner that would find it. To read it, you would need a primer, a biological password. For the ultimate security, we're seeing the rise of molecular blockchain. By linking a unique chemical hash from a vial to a digital blockchain, we create an unforgeable seal. You can't hack the liquid, and you can't fake the blockchain. It's the first time a physical object has a permanent, verifiable digital twin. So where are we really? If silicon computing in 2026 is at its peak, molecular computing is currently operating in its version of the late 1950s. We are in the mainframe era of biology, where a single computer would fill a whole room. Right now, we can write DNA at roughly a rate of 1 gigabyte per day on a high-end machine, and it still costs roughly $500 to $1,000 per gigabyte. But Carlson's law, the biological equivalent of Moore's law, is moving significantly faster. We are currently packing 5 years of silicon progress into a single year of molecular research. By 2030, we expect to hit the archive pivot, the point where it becomes cheaper to store 100 years of data in a vial than on a traditional server. Expect to see this hit the enterprise market, big banks and government archives in the next 3 to 5 years. This isn't just theory. In May 2025, industry giant Twist Bioscience spun out a storage division into a standalone company called Atlas Data Storage, launching with $155 million in funding. They recently announced the Atlas Eon 100, the industry's first scalable DNA archival service, claiming to store up to 60 petabytes in a single device the size of a coffee mug. Meanwhile, startups like Catalog DNA are moving beyond storage into DNA computing, using molecules to search through massive databases without ever turning them back into bits. And with the DNA Data Storage Alliance, which includes names like Seagate, Western Digital, and Microsoft, the titans of the old world are already building the standards for the new one. Molecular computing won't replace your RAM or run your operating system. Instead, it opens doors to the impossible. Planetary scale archives, maintenance histories embedded into the paint of airplanes, biological sensors that calculate a diagnosis inside your bloodstream. We are witnessing the end of the machine era and the start of the biological age. The future of data isn't just digital, it's alive. If you could preserve one piece of human history in a million-year vial, what would it be? Let me know in the comments. I'm Dan, and I'll catch you in the next one.